Hello, everyone. My name is Yahui Sun. I'm from Renmin University of China, and I'm a first author of a paper titled Hunting Temporal Bumps in Graphs with Dynamic Vertex Properties. Thank you for listening to my talk today. In our paper, we focus on graphs with dynamic vertex properties. So, what are graphs with dynamic vertex properties? In practice, we often have a graph where vertices exhibit a property of interest dynamically. For example, we may have a Wikipedia graph where vertices represent Wikipedia pages that are viewed a large number of times in some hours, but not in other hours. In this figure, for each Wikipedia page, there is a corresponding timeline. The green color in the timeline means that the corresponding Wikipedia page is viewed a large number of times. Two pages are linked to each other when there are links between these two pages. Given a graph where vertices exhibit a property of interest dynamically and a time interval composed of multiple time slots, for example, multiple hours, we consider a vertex as created in a time slot if this vertex exhibits a property of interest in this time slot. We further consider a number of times that a vertex is created or not created in a time interval, and a number of time slots in this interval in which this vertex is created or not created. Then, an intuitive problem is to find a pair of a connected subgraph and a time subinterval that contains as many created states of vertices as possible, and as few not created states of vertices as possible. That is to say, the discrepancy between the number of times that vertices in this subgraph are created and not created during this time subinterval is maximized. We refer to such a pair of a connected subgraph and a time subinterval as a temporal bump. We refer to this problem as a temporal bump hunting problem. Solving the temporal bump hunting problem is to identify where and when a property of interest occurs frequently. For instance, in a Wikipedia graph where the property of interest is a large number of time page views, solving this problem is to identify a cluster of closely related pages and a time subinterval, such that these pages are intensively viewed during this time subinterval. The existing researches on static bump hunting are closely related to our work. The topic of static bump hunting originated in the field of high-energy physics half a century ago, and is to find regions of static datasets where a property of interest occurs frequently. In particular, the problem studied by Jonas, etc. can be seen as a static version of the temporal bump hunting problem. That is to say, we consider a graph where each vertex is either created or not created, regardless of the time, and the objective is to find a connected subgraph, i.e. a static bump, where the discrepancy between the numbers of created and not created vertices is maximized. We refer to the problem as a static bump hunting problem. The existing algorithms for solving the static bump hunting problem do not suit hunting temporal bumps. Specifically, due to a neglect of dynamical query states of vertices, this algorithm can only hunt static bumps in a single time slot. We cannot use this algorithm to hunt temporal bumps by simply hunting static bumps in a time slot by time slot way, since the static bumps in different time slots may not share vertices with each other. And as a result, we cannot combine static bumps in different time slots together as a temporal bump. An intuitive idea of adapting this algorithm to hunt a temporal bump is to first hunt a static bump, i.e. a connected subgraph, and to find a time subinterval such that the pair of this subgraph and the time subinterval maximize the objective value of the temporal bump hunting problem. Then, this pair of subgraph and time subinterval is a hunted temporal bump. Theoretically, these adaptations cannot achieve non-trivial guarantees of solution qualities for hunting temporal bumps. Practically, our experiments show that these adaptations cannot hunt high discrepancy temporal bumps. As a result, new algorithms are required to meet the challenge of hunting temporal bumps. In our paper, we focus on developing new algorithms for hunting temporal bumps in graphs. First, let us formulate a temporal bump hunting problem formula. Given a time interval t of m continuous time slots, we consider an undirected graph G, where V is a set of vertices, E is a set of edges, and eta is a function which maps each vertex V to a set of m Boolean values eta V that correspond to m time slots in T and are referred to as query states of V. For time slot Tx in T, if eta Txv equals 1, then V is queried in Tx, which means that V exhibits a property of interest in Tx. Otherwise, V is not queried in Tx, i.e. eta Txv equals 0. These dynamical query states of vertices reflect the fact that vertices often exhibit a property of interest dynamically in zero graphs. We refer to a connected subgraph of G as a component of G. We define a temporal bump as a pair of a component and a time subinterval, i.e. the pair of a component C of G and a time subinterval Ts in T. Given a temporal bump CTS, we refer to PCTS as a number of times that vertices in C have been queried during Ts. Similarly, we refer to NCTS as a number of times that vertices in C have not been queried during Ts. Since each vertex has Ts query states during time subinterval Ts, we have NCTS equals Ts multiplied Vc minus PCTS. We define the temporal discrepancy of C during Ts, i.e. the temporal discrepancy of the temporal bump CTS, as dCTS equals PCTS minus NCTS. A temporal bump with a high temporal discrepancy corresponds to a region of G and a time subinterval, such that the property of interest occurs frequently in this region during this time subinterval. We define a temporal bump hunting problem as a discrepancy maximization problem as follows. Given a time interval T and a graph G, the temporal bump hunting problem is to find a pair of a component C of G and a time subinterval Ts in T, i.e. a temporal bump CTS, such that its temporal discrepancy dCTS is a maximum. After formulating the temporal bump hunting problem, we prove that this problem can be transformed to a temporal price collecting standard tree problem. Let us introduce the temporal price collecting standard tree problem as follows. We consider a time interval T and a graph G dash, where C is a function which maps each vertex V to a set of m non-negative values CV that correspond to m time slots in T and are referred to as vertex price. And similarly, C is a function which maps each edge E to a set of m non-negative values CE that are referred to as edge costs. Given a time interval T and a graph G dash, the temporal price collecting standard tree problem is to find a tree theta of G dash and a time subinterval Ts in T, i.e. a combination of theta Ts, such that the weight of this combination, namely WTS theta, is maximized, or the cost of this combination, namely CTS theta, is minimized. These two objectives are equivalent. After introducing a temporal price collecting standard tree problem, we propose several algorithms to solve this NP-hard problem. First, we propose an approximation algorithm Mira. It solves a temporal price collecting standard tree problem by first compressing temporal vertex price during every time subinterval to static values, and two, solving the static price collecting standard tree problem for its values during every time subinterval. Since it is too slow to conduct this process, we develop new branch and bound techniques that effectively accelerate the above process. Mira has some approximation guarantees. First, it has an approximation guarantee, a guarantee of 2 with respect to minimizing CTS theta for solving the temporal price collecting standard tree problem. Second, it achieves a non-constant approximation guarantee with respect to maximizing resolution weight. Mira does not scale well to a number of time slots. since it computes all time subintervals, while the number of time subintervals increase quadratically with the number of time slots. To overcome this weakness, we propose another approximation algorithm, S-mirror. The idea of S-mirror is to select and compute a nearly linear number of time subintervals in such a way that for any time subinterval Ti, there are two selected time subintervals such that the combinations of these two is Ti. S-mirror achieves non-trivial approximation guarantees the loser rules of mirror. To further push the limit of algorithmic efficiency while maintaining a practically high solution quality, we ignore non-trivial approximation guarantees and propose two faster heuristic algorithms, H-mirror and HS-mirror. Motivated by the observation that real bumps mostly contain created vertices, i.e., vertices that have been created at least once during a given time interval. The idea of H-mirror and HS-mirror is simple and effective. Instead of computing all vertices, only compute the created vertices and their close neighbors. We compare the proposed temporal bump hunting algorithms with the adaptations of the existing static bump hunting algorithms using 3 zoo datasets, New York, Reddit, and Wikipedia. In the experiments, we observe that the proposed algorithms hunt bumps with significantly, sometimes an order of magnitude higher discrepancies than the baseline algorithms. Meanwhile, the proposed mirror and S-mirror are often slower than, while the proposed H-mirror and HS-mirror are generally faster than the baseline algorithms. In the end, we conduct several case studies and show that hunting temporal bumps can retrieve information from different types of graphs with dynamical vertex properties. Specifically, we use the Wikipedia dataset to show that hunting temporal bumps can help us analyze our attention on the internet, while we use the New York dataset to show that hunting temporal bumps helps thread upon the dynamics of a city. So this is our work hunting temporal bumps in graphs with dynamical vertex properties. Thank you for your time.